ready to go live. Hey, I gave you guys an impromptu assignment at the end of class last time, and then I forgot to put up the poster. But who made up a haiku? Want to share? Me? Yeah, sure. Here, you can get a microphone.
All right. My haiku was feed, speed, depth of cut, important parameters, operators note.
Can I say mine? I can say mine? Holy shit. Yeah. What is that?
Thank you.
Yeah. Feed, speed, depth of cut, critical parameters, smooth operation. Yep. Did you make it?
I don't.
Oh shit. There's a bullet. There you go.
Going back down.
Yeah.
Here you go. Here's a mic.
Oh.
This I think I missed the point, but I said the juxtaposition of machine spindle is truly inspired. I was trying to use vocab juxtaposition.
Go for it.
Yeah. Which was in here? The powerful tools cut fast and efficiently, sound like jet engines.
Anybody else want to go? All right, one last one, then we'll do some more at the end.
Spindles tend to spin. Adequate normal force, key. Not enough, it's over.
Yeah, there you go. All right. And so doing these haikus, it helps us sort of stay focused, get our mind wrapped around it. Sorry, I didn't put in a little thing for you to submit those. But then if you didn't make one, you're off the hook. Put this up here. All right. So I promised that I'm going to try today to do 2 days. Sorry, this week I'm going to try to do 3 days worth of lectures in 2 days. So I'm going to talk really fast. Everybody good with that?
Not
Hey, who's
fast.
listening to one of my videos? Who's watching one of my videos? Display at 2x speed? I always do. When I go back and go through the videos, I always play at 2x speed. And I think then sometimes I can go faster. So recommended. All right, so I think where we ended up last time. We were talking about this idealized turning operation. You can draw it a couple ways on the board here. Right, so we have our bar stock here. We're holding it, we're spinning it this direction. Right, we're spinning it this direction. We've got a tool here. Right, and so we're feeding the tool in this direction. Everybody follows me? This is what we had, right? And so when we do this, we feed the tool in this direction. It actually makes these little bumps on the surface. Little valleys on the surface as we do that. This is actually a 3D printed model of that process, of the workpiece rotating, the tool feeding along there, and the surface that it makes. What I'm going to do is I get 2 of these. I'm just going to start passing them around the room. Once it gets sort of finished passing around the room, just keep passing it around the room. As we go through today, yeah.
Oh yeah, those breakers aren't they only like a smooth one?
It sort of could be like that. It's very similar to a threading operation.
Right.
As it gets finished, just keep passing it around. It'll be useful. It'll be useful to have it as a reference if we do this. Right. So we've got this. Now, if we look at the end view of it, we've got this. Right. So we've got our initial diameter, we've got our finished diameter, our tool here is down here. So this is tool, this is tool, right? So you can see how to transition from here to here. Does that make sense? Okay. So so this is our spindle, this is RPM, right? And so this is RPM. And what's the units for RPM? It's revolutions per minute.
Revolution. I think that's what it stands for.
Right. Revolutions per minute with units for RPM. Now, if only that was a massage chair working on us right now. So we got our RPM. But what we really care about, so as this tool comes around, a chip forms, right? And so that chip right now in this orientation is going straight out of the board action. Done. That chip forms here, and it flows this way, along the edge of the tool. This top surface of the tool here, that the chip slides along, is the rake face of the tool. So we call it the rake face of the tool. So this line here represents the rake face of the tool. Does that make sense? This geometry gets a little bit confusing sometimes. So we got this stuff moving along. Now this distance between the little bumps, what does that equal to? Yeah. It equals your feet in what units? The distance equals your feet. What are the units of? Feet per minute is distance per revolution, actually.
Nice catch.
So it's distance per revolution. So we would do inches per minute here. So inches per minute is our feet. Or sorry, inches per revolution. You can convert inches per revolution into per minute if you know the RPM, right? Let's just cancel the units out. And so when we visualize it and we talk about it, sometimes we talk about inches per minute as our feed rate. But what really matters is inches per revolution or distance per revolution. It would be millimeters per revolution or even metric units. All right, so this is our feed. It's in this direction, in distance per revolution. Now, what all the cutting happens though, what we really care about is the surface speed, correct? And so what are the units for surface speed? Yep. Feet per minute. So our surface speed is in feet per minute. And so in this drawing right here, that surface speed is sort of in and out of the board. Right? It's this direction. In this drawing here, that surface speed is right here. It's that direction. It's the vector of how fast this diameter is going past the cutting edge. So you say this diameter, I did a rate, right? So here's the minimum, here's the maximum, use the average. What I usually use when I'm doing a calculation like this is I usually use the one that would be worst if it was bad. So if I'm worried about too fast, I use the big one. If I'm worried about too small, I use the little one. But in general, you can use the average of those two. And so what's this distance here? Reasons. What is it? That's the depth of cut. Right? Okay, so that's equal to this distance here. Right? And the initial diameter minus the final diameter is 2 times the depth of cut. Right? So we got all that geometry of this. Then we got one more view that's really important to us. And it talks about the physics of what's happening to make the chip occur. We can all visualize this, right? We can turn the workpiece, we can put the tool through the workpiece. Now what I want you to do is sort of lay down on the floor here so that you're looking at it. Yeah, I can't really draw an eye. But you're looking straight at that edge. Okay? We're looking straight up that edge. So we're looking straight this way here as that happens. Yeah. You look at our eyeball is right here. Looking straight that way. What we get is
What is that?
the hammer.
Sounds like
Or an air
massage chair
compressor.
or blood pressure machine.
This is an air compressor. No, there's heaters out there. Air compressor will just shut off. I still think it's a hammer.
It kind of sounds like a blood pressure machine.
Tool. Keep on making it simple. And I start here. So I've got tool. I've got workpiece. I've got chip. Workpiece here. Workpiece here. So we've got, if we're looking straight down that edge, this corner right here, the apex, there is the edge we're looking at. So we're looking straight down that edge. And this is workpiece. This is chip. And this is tool. Right? We got three things in our system that we can care about. Did I ask you to do me a favor? It depends. You said that? All right. All right. Give me $50. All right. So the favor I want though isn't $50. Is can we assume steady state? Can we assume that there's no acceleration at this point? Because if we assume that there's no acceleration, then math is so there's going to be weird stuff that happens during acceleration. And I would rather not model that on a blackboard. Is that okay? So we're going to assume that we're in steady state. And so we're in steady state, there's no acceleration. That means all the forces balance, right? We did physics one. Possibly in this room. Right? Did I tell you the story when I was visiting another professor in their class? And a student asked him a question, and he looked at the student and said, "Did you take physics one here?" And the student said, "Yes." And the professor said, "You should ask for another guy." It was a question about this topic. It was similar to this kind of thing. All right, so let's assume steady state. Let's assume, okay, so what does, nobody else wants to look at it, I can grab it and I can toss it later. That's fine. What does power equal again? Yep. Power, well, here, you better, don't close your eyes today. What does power equal? 4 times velocity. Right, so power equals 4 times velocity.
Oh my god. Who did that?
The power equals 4 times velocity. Where do we have velocity? Now we don't have acceleration. We already said that. But where do we have velocity? Yep. From the rotation. Give me another one. I can do it again. Might be just as dangerous though. I think we should go through one safety glasses. We'll do that one after I step on. All right. So the velocity comes from the rotation, right? So we got our RPM going right here. And so that's causing the velocity. It's that vector just pointed straight down above me. So that's It's relative motion, right? Doesn't matter if it's the tool or the workpiece that moves. No, it's relative motion. So for this example, I'm going to draw the workpiece moving. We might reverse the vector later and have it do the tool. But the workpiece is going like this, right? And we know that the power of the spindle is going to have some impact on a force that lines up with that axis. But let's just look at what's happening here first. So we've got the workpiece going that way. The chip is going this way, right? The chip is pressing on the tool right here, right? The chip has to have some force that's pressing on the tool in that direction. Does that make sense? Pushing against the tool, which means if it's moving this direction and it's pressing this direction, there's got to be a frictional force, right? Has to be. And so the frictional force is going to be opposite the direction of motion, pushing on the tool in the down direction. Which means something in the machine tool has to want to push the tool in the other direction, right? So that'll be the combination of the X and the Z servo motors that are pushing the tool back the other direction. Because we said steady state, we said no acceleration. Oh, this is pretty boring because it's all lined up even. It turns out when we do our cutting here, we almost never plow straight in like this. Did you guys see this in the lathe? Almost always, this tool has an angle here. Can we call that the side edge cutting angle? Because that's what we're going to call it. So if I put that angle on the tool, and I call it the side edge cutting angle, I still have my chip forming here, right? Mm-hmm. Oh, so if you do the chip forming here, and so changing that angle doesn't impact this drawing, does it?
Yeah. I mean, wouldn't the same thing happen on the other side? Working
Well, this one's only on one side. Yeah, I should have changed both sides of this. I agree. Good catch. So bad catch on that part. Good catch on the drawing. Yeah. I called it the side edge cutting angle. And so here, if we're looking at this, it's like tipping the tool this way. Right. So we can change the side edge cutting angle of the tool. And but that doesn't really change this drawing. What else can we change here? Is we could change the rate angle. We could change how much tipped it is this way also. And here, that would be like tipping the tool even out. So we change that rate angle. So we change that rate angle. This drawing we change the rate angle of this drawing. What we do is we make the tip back a little bit. And the chip's gonna form and it's gonna flow that way. And so we'll call this a positive rate angle. And we measure it from the vertical. And we use alpha. So positive rate angle is alpha, it's this angle right here. The chip's going that way, and so in this situation now, my friction force has to be that direction, because it has to be lined up with that rate face of the tool. The other situation, it was straight down. It makes it so all the vectors don't end up on top of each other like this. It also tends to make the cutting force lower, which is good too. Why are we studying all this? We study all. Why did we want to study physics of machining? When did most of the research get done? Yeah. Yeah, we want to built stuff to blow people up back in World War II times, right? So we wanted to get more efficient at making stuff so that we could get more efficient at killing people, but that's a whole different story. We did the math. All right, so picking our angle. Oh, people done all this research. Okay, so we keep that angle. I don't want all the vectors to line up on each other for the illustrative purpose here. So I knew it's a positive rate angle. That means that friction force has to be pointed in this direction, right? What's a good variable for friction force? I like that. Let's use that. All right, so we got our friction force line up there. Now, what was the other force that has to be? There has to be the normal force of the friction, right? Because that's what causes it. So we got a force normal to the friction. Anybody want to call this one N? Sweet, let's call it N. All right, and those two forces add together, right? Around here. Here. And those two forces add together. The resulting force. I have no idea why we decided to call it P, but in the literature we always call it P. So we've got our resultant force. It's the addition of the normal force and friction force. Now, if our operation is in steady state, there's no acceleration. That now describes the forces acting on the chip or on the tool or on the workpiece. Right? That total force is the force. But power equals force times velocity. We don't know the velocity of the chip. What we do know is the velocity of the chip is not the surface speed. So our surface speed is that direction, right? We know the velocity of the chip is not the surface speed because we're mushing material together to make that chip. Right? We saw the video last week where we had workpiece material with all these different grains in it, and they're all sort of symmetrical, and we move in this direction towards the tool. And then in the chip, the grains all look sort of like this. Right? So we're taking energy and mushing the material together. It's going to slow down that chip as it moves out. We don't know how much it slowed it down. But we do know this velocity, right? Because this velocity equals revolutions, or distance per revolution, right? Equals pi d with the 4 in there, right? We know what that surface speed equals. And we know that power equals force times velocity. So the power that goes to the motor that causes the spinning has got to add together with the thrust force to make the same result vector. Because there's no acceleration. It's not flying across the room and accelerating out of it, except when we have the wrong parallels, right? It's not accelerating out of the machine tool. Right? So, if we were to take and break down the force, this resultant force, into a force that aligns with the direction of motion, I'm going to call that FC. That's the cutting force. And we can have a thrust force. And that thrust force is going to come from the servos to the X and the Y, or X, Y, and Z direction of the tool motor. Right, moving the stuff around. And we'll call this FT, the thrust force. So we've got a cutting force that lines up here. And we know that this times velocity equals the power that we measure at the spindle. Sort of. It'll be a little bit less, right? It'll be a little bit less because some of the power that goes into that spindle motor is going to become heat inside the spindle motor. Some of it's going to go to frictional losses in the drivetrain of the machine. But most of it It is some efficiency factor that you could use to estimate how much that is. But most of it goes to here to make the chip form. So we know something about the chip sliding on the tool. We know something about the geometry of the tool in the machine and the forces, how the forces line up there. The other thing that we care about here, though, is, and this is what's going on right here in this shear plane. And that's where the workpiece stops being a workpiece and becomes chip. And we're mushing stuff together there. And so if I asked you to cut aluminum or stainless steel, which one's harder to cut? Who said stainless steel? What do you say? You're going to say stainless steel also. Who says aluminum? Why is aluminum harder to cut?
Well, it's harder to do, right? Like,
It does get gummy. It's harder to evacuate it out of the flukes on the end mill. It turns out, and I used to think stainless steel was hard to cut. Here's the thing. Stainless steel takes more energy to cut. I think it takes like 7 times more energy. But from my perspective as the programmer, all I do is tell the game software which my data is right. So for me, neither one is harder to cut. But stainless steel takes a lot more energy to cut. So what's causing that is the differences between those grain boundaries and the stuff that's happening in the material. Yeah.
You say there's no energy to cut because the materials are physically harder, right?
It is also physically harder, but that's a different bulk property. Yeah.
are you feeling over like harder to cut just because of
It can be more difficult to cut because of dealing with the chip.
it's soft?
It's harder because so when we're fixturing, we clamp on the part to hold it in place. And what keeps it from pulling out of the fixture is friction. And so we have to clamp harder to get the same frictional force. Or possibly. It's more squishy. So we might damage the parts by clamping harder, get more frictional force. So more difficult. So it's a trick question which one's harder to cut, right? Because it depends on what your perspective is. So you don't like the fruity ones?
No,
Somebody else should answer questions. But when we're interested, and we did all this to learn about how to cut stuff, so we can cut stuff better, so that we could be better at doing this. And so when we're interested in the differences between the material properties, what we really care about is how much force did it take to shear those grains from each other. How much force did it take to do that? And since we want everything to add together, it's take that much force with it. If we want everything to add together, yeah, my key is in the wrong direction. But the force that lines up with the shear force, it's got to be a normal to that also. And so we've got 3 orthogonal force systems. And depending on if we're interested in the bulk material properties, if we're interested in the tool chip interaction that's happening right here that slides along, we can convert between those force systems. Is that fair? Right. And so how do you convert between the orthogonal force systems? How do we convert between orthogonal force systems? I'll leave that for a question for the next class. The bonus points would be know how to convert between orthogonal force systems for the next class. We've got the let's see. What else about geometry do we want to look at here? We've got 3 force systems. We can use the different force systems depending on what we care about. Let's talk a little bit more about the geometry of the pattern. So, I'm going to redraw this so it's not so messy. We've got our workpiece, our chip. We've got a tool. We've got a chip interface here. That's our rate piece of the tool. Okay. Surface on the workpiece. Okay, so we'll call this the uncut chip thickness. That's the material that is about to become chip. Is that fair? Our uncut chip thickness is the thickness of material that's about to become chip. And we've got our chip here. And we've got, we'll put a T2 there. That's the thickness of the chip. They won't be the same as each other. Is that fair? I suppose. Maybe they do the same as each other. All right, maybe. Yeah. No. If there's a cutting force, they won't be the same as each other. So only if they weren't actually part of the same material to start with could they be the same. Then it would be like we were just unwinding a spiral. Wouldn't be the same. All right, so we got our uncut chip thickness, we got our chip thickness. We got that shear plate. And we got our breaking angle, right? This is alpha. This is our rate angle. So this angle here is our shear angle. And so as that shear angle changes, it's gonna be impacted by the bulk materials of the bulk properties of the material, right? It's gonna be impacted by that. It's also gonna be impacted by our rake angle. Does that make sense? So if I change that rake angle, it's gonna cause this plane to shift. When we do that, you can actually, by studying the chip and knowing the uncut chip thickness, you can learn about those bulk properties of the material, because we could show geometrically the ratio of the uncut chip thickness to the chip thickness. It's called RT. The RT equals. So we can show that, so using that, I am not interested in that much. I can share that with you. I'm not. Especially equations like I'm talking about. So I know the equation exists. And I know the importance of the equation. And when I need to use it, I look it up. So let me use my reference here. If we want to know the shear angle, we can say that the tangent of that shear angle equals RT. That's the ratio of chip thickness. RT cosine alpha. So we can show through geometry that this is true. And from that, by observing, so this is where the science part comes in. We do experiments, and we vary rake angles, and we vary materials. We can learn about the bulk properties of the material so that we can then use that information to predict what the forces would be in the future. Yep.
Would that include something like the vibration of the tool off the particular material? Like when you spin it?
We tend to ignore vibration in these calculations because it makes the math harder. I do know people that have gotten entire PhDs just trying to understand one phase of formula vibration. And they get the PhD, but I'm not sure they really understood it. So yeah, it's nice to ignore those things. All right, so we get this from geometry. What else do we get from geometry? What is that T1 equal to? How do we know what T1 is? If we go back to the situation where that side X cutting angle is 0, T1 equals to T ray, right? It equals the distance that the tool moves over each revolution. We do that, but since we almost never have a side X cutting angle of 0, what does T1 equal? Equals T1, since we draw on this one, T1 T times cosine of the side edge. So P equals P1 equals Q times cosine times cutting. So when side edge cutting angle equals 0, what's cosine equal? 1. Yeah, perfect. But I got the equation right. Didn't even look that up. Just here. That's why I have to check it out. All right. So Q1 equals that. So we got the feed. We did pick the feed, right? Yes. Okay. We need to pick the feed. T1. All right. So we've got this, and we get to pick. Do we get to pick the shear angle? We get to pick the shear angle. Yes. No. We don't get to pick the shear angle. The shear angle gets picked, well, not directly. Yeah.
Well, doesn't rate have anything to do with?
You do get to pick the rake angle.
Right, does the right angle have anything to do with the shear angle as well?
It does, right? It has to do with the shear angle right here, but we learn this by observation. Because we don't pick T2. How do we know what T2 is? Somebody that has not answered a question yet today. I'll show the piece of candy, whoever the piece of candy gets. Somebody who has not answered a question today. You haven't answered a question today. What was the question? Somebody I forgot.
How do you put T2?
How do you know what T2 is? All right, somebody who has answered a question today. How do you know what T2 is?
So basically, bring T2 on the side of the RT.
Oh, I don't mean how to solve the equation. How do you know what it is? Oh, you're doing the experiment.
Just the width of the chip,
Yeah, you pick the chip up out of the machine
yeah. And you measure it.
and you measure it. That's how you know what T2 is. So that's what makes it an experiment. All right, so we got all these things. Now, why did we do all these experiments? Why do we do these? Why do we do these experiments? Well, some of us do experiments because we love the science of it, yeah. But we do the experiments so we can make stuff better, right? But this particular thing, we'd like to be able to estimate how much power it's going to take, right? We can estimate how much power it's going to take. We can also estimate what the cutting forces are going to be. We can estimate how much power it's going to take, what the cutting forces are going to be. We can design manufacturing processes that don't cause explosions, except for explosive forming. In which case, you're using the explosion to shape the material. I heard a rumor that the Corps of Engineers, is anybody here like Army or ROTC? No? Air Force. Yeah, they don't have a Corps of Engineers. You just wait for them to come build your runways. core engineers aren't. Anyway, I heard a rumor that back in the '60s, they actually had a manual for nuclear excavation. When you literally had to move them out. It was a rumor. I've seen it. I've read it. But what a cool rumor. You take a couple nukes and move that mountain down the way, you march your division through. There seems to be some problems with the whole premise, but yeah. So we don't want our manufacturing processes to explode unless we're doing explosive forming. All right, let's get back to the power side. Let's go down there.
Who did that? Somebody's gonna figure that out. Yeah, who did that?
All right, so back here on the power side, let's just step away from understanding the geometry for a minute. Let's just think about the machine process in making the part. So we already know that power is going to depend on something to do with the material, some material property. Right? And so I'm going to call that a, let's call it. And so I'm going to say that this is my sort of the intrinsic power variable that impacts by this material. And so you can look these KP values up in a chart if you've done a bunch of experiments in your chart. Does that make sense? So what you do is you take a bunch of different materials, keep all the other cutting parameters the same, and you measure the power. And so that you can see how does the power change based on the material. So that's how you come up with this program. Right, so we've got our power that depends on the material. What else do you think the power of the cut? Which is the power that we're using for force times velocity also. What else do you think that power depends on besides the bulk material properties? Yeah. No, we're working backwards to get to that point. So that would be a circular argument. Yeah. Something involving velocity. You would think so. But what else do you think it would depend on? I mean, depending on which units you're using. If you use RPM, then yes. But if you're just looking at surface speed, not something the position of the tool. So yeah, there's going to be something that depends on the tool, and we'll call it like a tool sharpness factor. So how sharp is the tool? It's you've all done this. You cut steak with a butter knife and butter with a steak knife, right? So it depends on how sharp the tool. Because I mean, you've experienced it actually. Like, here's a cool experiment you can do at home. I owe you one of these. Here's a cool experiment you can do at home. Get some butter. Cut a stick of butter in half. Leave half of it in the fridge, leave the other half on the kitchen counter for 10-15 minutes. Then take a knife and scrape across the top of the butter. And when the butter is really hard, this is what you have to do to butter your toast, right? Scrape that knife across the top of the butter. Watch as the chip forms on the edge of the knife. That part of it, so if the knife is straight up and down, you're moving like this. That part of the knife is straight up and down, that's the right face. That little corner at the bottom, that's the cutting edge. And butter forms chips exactly the same way steel does. It takes less force. So you do that little experiment at home. So how sharp the tool is. So let's just say tool sharpness. So unit energy, tool sharpness factor. Yeah.
So it's sharpest tool, but also would that also include the like materials, state, etc. Because
Of the workpiece?
Yeah.
Yeah, so changing the temperature can definitely change that unit power.
it's
But changing changing the temperature is it would be like heating up the workpiece material in a furnace before cutting it. It would be the same as cooling down the thing. Yeah.
What the time in a given location?
So the time it's really how much cutting are we doing, right? And so what's actually cool is it's the volumetric material removal rate, and we usually call that Q. Volumetric. The volumetric material removal rate is really how fast you put chips in the bucket. How fast are you removing material from the workpiece? And so that's why if you use RPM for your units, then the speed does matter. But what really matters is the depth of cut in the heat rate. It's how far down are we? If it's a milling operation, like how far down are we? How far in are we? And how fast are we going through it this way? That's our volumetric material removal rate. And then there's fluids. So in fluids, you do a lot of equations, right? Yeah. Right. And most of the equations are based on experimental results. And what do you do when the experimental results do not equal the theory? But they're close. They sort of parallel the theory, if they don't equal. Anybody remember? All include experimental science students. Yeah. Well, we could use chalk, but usually we use fudge. And we create a fudge factor, and we come up with a variable that sort of describes the difference between our theory and the end result, right? And it turns out when they did that here, they realized that the fudge factor actually had to do, it was correlated with heat rate. And so there's another term here, I think it's C. I don't remember what all the terms are, we'll look them up in the book in just a second. But there's that other term there that's C, that sort of, it depends on how fast you're going. If you're going slower, the data lines up this way. If you're going faster, the data lines up this way. But they were able to show that experimentally. And so, how do you get all this data if you want to estimate the power?
To multiple trials.
You could do an experiment, you could do multiple trials. I'm lazy. How are you going to get it? I'm going to go to a reference guide, and I'm going to use the Machinery Handbook. Horrible throw. Horrible throw. I'm going to do the Machinery Handbook. And it's available for free at the guide library. You can find it by going to Google. Typing WPI library. I don't have a WPI library. It will bring you to a webpage that purports to be the WPI library webpage. There'll be a search bar sort of in the center of that screen. Has anybody seen that screen before? Yeah. Type Machinery's Handbook. There. I have learned through multiple uses that you don't actually have to spell it correctly. It's good enough to get you there. I think the latest edition is the 31st or 32nd edition. I use the 28th edition because I happen to have the large print version of it. And in the 28th edition, at page 1054, it won't be the same as the other one, but it doesn't matter which edition you use. You can find where it talks about power and machining, And there are tables for all these different factors. I have a fabulous YouTube video that shows you how to do this. I mean, how to go look it up in the library. So if you have trouble, I would post a link to that YouTube video. It helps you learn how to look up these parameters so that you don't have to do the experiments yourself. All right, so I think today we got an understanding of the geometry of how the chip is formed. Is that true? Good. And we got a sort of a top level thought-based understanding of why power is different with different materials and with different setups and things like that. Is that fair? And we remember that power equals force times velocity, and that T1 equals T times cosine sinus cutting angle, and that tangent of the shear angle equals R T cosine alpha over 1 minus R T sine alpha. We got so this geometry of how everything ties together. On Thursday, you remember the class tomorrow? On Thursday, you remember that you're going to have figured out how to translate orthogonal force systems, right? What's the mathematical technique that we use to move from one force system to another when they're orthogonal? Right? Okay? And we're going to go into understanding how all of those different forces affect us and how they affect the part.
The third force system was the shear, right?
The shear, lined up with the shear length. Thank you very much.